The investigation of several icing accidents during the past few years involving turboprop aircraft has implicated ice buildup on the horizontal stabilizer as the cause. The result? An uncommanded pitch down of the aircraft nose or other severe control problems when the flight crew extended flaps. Accident investigations revealed that in one extreme case, elevator forces exceeded 400 pounds. Many regional airline fleets comprised of turboprop aircraft fly at low and medium altitudes, right in the middle of the icing environment. With the increasing takeoff and landing cycles of turboprop flights each year, these aircraft are statistically more exposed to potential icing conditions for a greater percentage of flight time than aircraft flying longer and higher altitude routes. Most incidents of tailplane icing have involved regional airliners flying turboprop aircraft. However, large and small general aviation aircraft are also susceptible to ice-induced tailplane stall. In any case, the recovery procedures for tailplane icing are still not well understood. Although the chances of encountering a tail stall condition are infrequent, lack of understanding and awareness of safety techniques can have devastating results. At least 16 crashes have been directly attributed to tail ice, and perhaps many more. Often, the evidence is unrecoverable. Current icing training focuses on ice formation on the wing and fuselage. Some time-honored procedures, such as increasing airspeed that work for a wing stall, may actually intensify a tailplane icing problem.
This video will probably dispel some long-held assumptions many pilots have about airborne ice. In addition, and more importantly, you will get the very latest information we have on tailplane stall. I have to admit, 15 years ago, when I first started flying icing research, I really wasn't fully aware of just how sensitive the newer, more efficient stabilizers are to ice accretion. Not only in ice collection efficiency, but just how close to or over the ragged edge pilots may find themselves to control loss.
So, what's being done to learn more about ice-induced tailplane stall? In 1994, the FAA asked NASA Lewis Research Center to conduct a comprehensive study to measure the aerodynamic performance and control degradation associated with ice-induced tailplane stall. The icing research team at NASA Lewis developed a tailplane icing program to address the FAA's request. This program drew upon NASA's unique icing experimental facilities, icing prediction tools, and technical expertise.
The tailplane icing program set out to provide an increased understanding of the aerodynamics of ice-contaminated tailplane stall. This information is to be used by the regulatory authorities and by aircraft manufacturers. But in the course of doing our research, we came up with some critical icing information that we believe is valuable to pilots and could very well prevent accidents and ultimately save lives.
Airplanes that have been involved in suspected tailplane icing encounters share some common design characteristics. Let's look at these characteristics more closely. Aircraft that use unpowered controls. In other words, those that rely on aerodynamic balance to keep stick forces neutral. Keep in mind, this is where the horizontal stabilizer has a fixed leading edge and the elevator is held in position by an adjustable trim tab. Large flap deflections, which produce large amounts of downwash, resulting in a high angle of attack on the tailplane. Aircraft that use de-icing boots as opposed to an anti-icing system. In most aircraft designs, the horizontal stabilizer has a sharper leading edge than the wing and is therefore a more efficient ice collector. To illustrate this phenomenon, 2 airfoils were placed inside the icing research tunnel at NASA Lewis. Under most icing conditions, observe how the sharper leading edge of the tailplane has collected a higher percentage of ice than the rounder leading edge of the wing. This means if there is any ice on the wing, there may be significantly more ice on the horizontal stabilizer. If you notice ice on any part of the aircraft, you should be aware that ice may already be collecting on the horizontal stabilizer. This condition is further complicated because pilots usually cannot see the tailplane from the cockpit. Tailplane stall due to ice accretion is rarely a problem in cruise flight. During this part of the flight, the horizontal stabilizer is not working anywhere near its performance limits. Consequently, flight crews may not have any aerodynamic clues that ice may be building up on the tailplane until the aircraft configuration is changed. The effects of ice contamination on the horizontal stabilizer are typically noticed during an approach, after flaps are extended, and when the aircraft is close to the ground. During this part of the flight, the horizontal stabilizer is working near its performance limits. If the tail stalls at this point, recovery is very difficult. Before we look at this in more detail, let's review the fundamentals of basic aerodynamics. In straight and level flight, the vertical forces acting on the aircraft are the weight, which acts through the center of gravity, the upward lift, which is generated primarily by the wing, and the downward lift generated by the horizontal stabilizer. The center of gravity, which is also the aircraft's pivot point, is almost always forward of the wing center of lift. The forces acting at these 2 points cause a nose-down pitching moment, which must be counteracted by the horizontal tail. To achieve the required downward lift, the tailplane is designed as an upside-down wing. When the flaps are extended, several things happen simultaneously. The wing center of lift moves aft, creating a larger nose-down pitching moment that the horizontal stabilizer must overcome. The tail angle of attack increases. This is due to the increased wing downwash, which naturally generates more downward lift by the tail. In addition, as the aircraft reaches equilibrium, more downward lift may be required. This is accomplished by moving the elevator toward the trailing edge up position. Consequently, the flap extension drives the horizontal stabilizer closer toward its stalling angle, particularly as the aircraft slows. This is when tailplane icing becomes a serious problem. A small amount of ice on the tailplane leading edge can interfere with airflow on the lower surface of the horizontal stabilizer, resulting in flow separation. This can decrease the stalling angle of attack and limit the amount of negative lift available. A sudden change in elevator hinge moment and forward stick force may overpower the pilot.
When the flow comes in and sees the ice, it separates. But what happens just downstream of that separation point? What's there? Something's got to move in and fill that void. Well, usually it's the flow. It'll wrap around and create a separation bubble. That separation bubble has a reattachment point. As the tailplane angle of attack increases, this reattachment point will move aft. If it extends over enough of the elevator beyond the hinge point, now you have a movable control surface that will fill that void.
So, what are some of the warning signs that could indicate a problem with the contaminated horizontal stabilizer? Individual pilots may perceive these warning signs at different times, depending upon the pilot's experience and icing conditions, the workload in the cockpit, and the intensity of the situation. Now, it should be noted that if you were flying on autopilot, you would almost certainly miss these symptoms because you would not get any tactile feedback from the controls. And here's what we found. Although these warning signs may vary slightly, depending upon the airfoil and the conditions. A lightening of the controls may be felt, specifically stick lightening in the forward direction. Difficulty trimming the airplane. Onset of pilot-induced oscillations. Buffeting in the controls, not the airframe. Remember, many times these symptoms are encountered when flaps are at full extension. In extreme cases, there may be a sudden pulse-forward stick movement, possibly very strong. The nose of the aircraft may suddenly pitch down, and it is very possible that this may not be recoverable on final approach because of the low altitude of the aircraft.
Symptoms of tailplane stall can actually be pretty subtle, or they actually can come right up and bite you. For instance, the normal progression is first you feel a lightening in the yoke, particularly in the forward direction. And this can lead to PIO, which is pilot-induced oscillation. And this happens because the control balance is changed. Now it's very easy to push forward on the yoke and much more difficult to pull aft, so you wind up with a pilot-induced oscillation situation. It can progress from there into the yoke actually trying to come out of your hands and go forward. You'll feel forward pulsations and forward movement on the yoke. The worst case scenario is where that yoke is actually snatched forward right to the stop, and you're unable to pull it back. As a matter of fact, in some cases, and in our case in particular, we've had force pressures of over 170 pounds of force in order to get the yoke back.
In order to measure the aerodynamic effects and control characteristics of tailplanes contaminated with ice, NASA conducted a series of flight tests in a modified de Havilland DH-6. To simulate various icing encounters, polyurethane ice castings were attached to the tailplane. The ice shapes were made from impressions taken from a full-scale DH-6 tailplane tested in the Lewis Icing Research Tunnel. The DH-6 was outfitted with instrumentation to monitor and record aircraft performance data, such as aircraft and tailplane angle of attack, airspeed, and tail surface pressure. All control surface deflections were recorded to measure the pilot input. Yoke and rudder control forces were also recorded. Video cameras monitored tufts attached to the lower surface of the horizontal stabilizer. Cockpit cameras captured pilot reactions and a view of the horizon during the maneuvers. So what did NASA researchers find out during flight testing? Results of the flight test reveal that there are 3 paths that can lead to tail stall conditions if the horizontal stabilizer is contaminated with ice. These are increasing flaps, increasing speed, increasing power. Let's take a closer look at the effects of each of these paths by reviewing some video recorded in flight by the research team. Now be aware, this work was conducted in a highly structured research environment with qualified test pilots and flight test engineers to interpret the many visual and real-time data cues that identify approaching tailplane stall conditions. Intentional maneuvers to induce tailplane stall are not recommended in a non-controlled environment. Here, the flaps were deflected from 0 to 40 degrees. Notice how the tailplane angle of attack becomes more negative and the tufts begin to destabilize. The yoke buffet indicates a separation and reattachment of airflow, making it difficult to keep the aircraft in pitch trim.
Judy, are you ready?
Yeah, records are on.
Okay, record.
With the flaps fixed at 40 degrees, as the speed is increased, the tufts at the leading edge are pointing upstream, indicating full reversal of flow. The tufts that are aft of the leading edge area indicate turbulent airflow on the rest of the horizontal stabilizer. As the speed continues to increase, flow separation and reattachment cause the elevator to buffet.
Tailplane 81. It wants to pitch over very badly right now. Pitch stability is very, very difficult. It's starting a small oscillation.
In this maneuver, there was no ice shape attached to the stabilizer. Power was increased slowly while the speed was held constant. Observe that there is very little tuft activity. Now watch what happens as the same maneuver is flown with an ice shape attached. Notice that even with the power at idle, the tufts at the leading edge indicate full flow reversal. The tufts aft of this area indicate minor turbulence. As power increases, the pilot brings the elevator up in order to maintain speed. The separation and reattachment of the airflow at the elevator trailing edge causes the buffet. Although the goal of the research team was only to approach a tailplane stall, the crew did experience a full stall during a maneuver in which power was increased. Let's take a look.
Very, very hard to control speed and even attitude in the airplane. Force is going up as high as probably around 80 pounds randomly, and I can't add any more power to it at this point.
Yeah, we've got...
There we are, we have to stop. Flaps up. They're already moving, okay? I started them up as soon as it went over.
The tail stall occurred to us in the process of performing a power transition maneuver. The control forces built very rapidly. The nose pitched over at a very high rate. We all got very light in our seats. The co-pilot and I immediately applied recovery controls. I pulled the stick full back. He immediately retracted the flaps, and I retarded the power. All this occurred in about 0.2 of a second. The nose pitched over at about a rate of 2 to 15 degrees per second and reached a nose-low attitude of about 40 degrees before recovery controls finally took hold and the aircraft flew out of the tail stall. We lost about 300 feet of altitude in the process.
So, what are some safety techniques a pilot can use to avoid a tail stall encounter? The pilot must first correctly diagnose the problem. Although the differences between tail stall and wing stall warning signs are subtle, the recovery techniques are quite opposite. With normal wing stall, the suggested recovery procedures are to add power and relax back pressure or push forward on the yoke, depending on trim. In an impending tail stall situation, the recovery is the opposite. Pull back on the yoke, reduce flaps, and on some aircraft, ease off on power. In the intensity of a busy cockpit situation, the pilot must be able to differentiate airframe buffet from yoke buffet. Now remember, with wing buffet, you will get feedback through the seat of your pants. Another clue in differentiating tailplane stall from wing stall is the aircraft configuration and speed. If flaps are lowered at the high-speed limit of flap extension and there is elevator buffet, chances are it is a tailplane icing problem. The higher the airspeed, with flaps extended, the more susceptible the aircraft is to tail stall. So, if the pilot determines that there is buffet or lightening of the controls, has difficulty in trimming, or is experiencing PIO, immediately pull the yoke back and retract flaps to the previous setting. And be judicious with power.
The no-brainer is to pull the yoke back. The problem is because of the high control forces, you may have great difficulty in getting it back. Also, raise the flaps to the last position. These two actions are universal in a tail stall situation. Our research also shows that you may want to be very judicious with the use of throttles. High power settings will make the stabilizer work harder and aggravate the tail stall situation.
With suspected ice contamination, apply power judiciously and maintain precise control of airspeed. And remember, avoid full extension of flaps. Even partial extension should be done at altitudes that allow recovery. Make pitch changes slowly, particularly nose-down movements. Remember, lightening of the controls or PIO could be an early warning of tail stall. Also, difficulty in trimming the horizontal stabilizer may be another indicator of a tail stall condition. One or all of these symptoms may be apparent. If the aircraft is equipped with a pneumatic de-icing system, activate the system several times to try and clear the ice. Land with reduced flaps if conditions permit. While large aircraft with hydraulic controls are less susceptible to tail stall, the tactile clues, such as stick lightening or yoke shake, are greatly reduced. This means that the pilot in this type of aircraft needs to be perceptive of the more subtle clues. For example, unusual trim settings, and also the possibility of pilot-induced oscillations. Let's go back and take another look at what NASA researchers experienced when they induced a tailplane stall and the corrective actions they took.
Okay, we're starting to get some very relatively high control forces. Oops, I got the speed down.
Full, all standing up, laying back down.
Very, very hard to control speed and even attitude in the airplane. Forces going up as high as probably around 80 pounds randomly, and I can't add any more power to it at this point.
Yeah, we've got...
There we are, we have to stop. Flaps up. They're already moving, okay? I started them up as soon as it went over. That's it, good. Good work. Okay.
All right, guys, good job.
That's about as far as we're ever going to go.
It should be noted that other aircraft with ice-contaminated tailplanes might not react to a power increase as dramatically as the modified DH-6 did. So, to protect your passengers, yourself, and the aircraft from encountering an ice-induced tailplane stall, remember these key points. Become acutely aware of the symptoms of tailplane icing, and be prepared to undo any configuration changes. Avoid the use of autopilot in known icing conditions. If equipped with a de-icing system, use it to clear even small amounts of ice, especially before extending flaps during final approach.
You can imagine an instrument approach in icing conditions close to or at minimums. You lower the flaps, the yoke starts shaking. If you misdiagnose this as a wing stall, you and your passengers could be history. Remember, you have very little time to correctly diagnose the problem and take the proper corrective actions.
When ice is a factor, there is more to consider than wing stall and drag increase. Be knowledgeable, be aware, and take the corrective actions necessary should you encounter tailplane icing. You don't want to be looked at as the probable cause in an aircraft icing accident. Remember, in almost all tailplane icing accidents, the cockpit hits the ground first.